Hello AP Stats students, I'm Mr. Sager, and this is the first of many video lessons that you'll be watching for AP Statistics. This one is on part one of the summer assignment. If you have any problems as you're completing this assignment, feel free to email me at gsager@tiaraschools.com. You can also join the remind.com messaging group by texting at SagerAP to 81010. We're going to be completing the first few chapters with this summer assignment. Some parts are a bit challenging, but overall the content's very manageable. And getting it done over the summer is going to free up time for us to do more of the activities, which is what actually makes the class fun. So to start, a frequency table organizes categorical data. So here we have information about the passengers aboard the Titanic. This is real data. Most of the problems that we deal with in this class will be based on real data. So the actual thing that we're looking for is what class they were in, and we have counts of each of those classes. This is a categorical variable because the data we're collecting is based on categories. Compare that to a quantitative variable where the data we'll be collecting will be based on a quantity or a numeric value. So categorical, non-numeric. If we want to make, instead of just a frequency table, a relative frequency table, whenever we see this word in front of it, we just switch everything to percentages. So we add up all these numbers, find out what's the total number of people on the Titanic, and then we switch each individual category to a percentage. So for example, 14.77% of the passengers were in first class. If we wanted to make a display of this graph, we want to make sure that our display abides by the area principle. And what that means is that the area of any part of our graph should correspond proportionally with the amount of data that it represents. So in other words, if we look at this second class boat, 285 people were in second class. Now, crew members had 885, and that's about 3 times as big. It's actually 3.1. So in this display, which does not abide by the area principle, we just made the length of this second class ship 3.1 times as large. And the problem is that the area of this larger ship is a lot more than 3 times the area of this smaller one. While it's a bit flashy to use photos of a boat in a graph to represent the passengers on the Titanic, we'll never do anything like that in this class. Instead, we stick to simpler options. And there's only 2 for categorical data. There's pie charts and there's bar charts. Here we have a bar chart. This is always going to abide by the area principle. Reason being that we make sure that the width of each of these bars is always the same. So that lets the height determine that area. So this bar for crew members will end up being 3.1 times the area for the bar for second class passengers. So that was a bar chart, and one of the identifying properties of a bar chart is that we have gaps in between each of these bars. And that's because the order down here doesn't actually matter. If we decided that we wanted to take the crew members and put them before first class passengers, that's okay. Compare that to a histogram, which is going to be coming up. In a histogram, the bars touch because it's quantitative data and we can't rearrange them. So if we were asked instead to make a relative frequency bar chart, just like when we were dealing with the tables, when we see this word, we just change everything to percentages. That's actually what this is here. It's been switched to percentages already. The one on the previous slide had counts on the left. And if you actually look at these 2 graphs, they're not any different at all. So switching from a frequency bar chart to a relative frequency bar chart doesn't change the shape at all. It just changes the axis. Next up, we have contingency tables, which organizes 2 categorical variables. So we still have our class across the top here. And in addition to that, we have survival status. Did the passenger live or die after the sinking of the Titanic? If we look across the margins, so across this entire row, we can see that there were 711 survivors and 1,490 passengers that died. We can also see totals for each class. For example, there were 885 crew members, and we can find specific instances such as 118 passengers were second class passengers that survived. Now for some terminology, we'll start with marginal distribution. If we're asked to find the marginal distribution of survival, it's exactly what it sounds like. We're going to go all the way over to the margins, and we're looking at these 2 numbers here. We're just going to take each of those numbers and divide them by the total number of passengers on the ship, and we get these 2 percentages. 32.3% of passengers survived, 67.7% of passengers died. We could find a marginal distribution of class by doing that same thing with these numbers at the bottom. If you're asked to find a conditional distribution, it's the same idea. It's just giving us some condition that we have to abide by. For example, find the conditional distribution of class for the survivors. In other words, we don't care about any of the passengers that died. We're only interested in the passengers that survived. So we filter it down to only include this row, because these are all the people who lived. And we do the same thing, except instead of putting that 22 on 1 on the bottom, which was all the passengers, we're going to divide each of these by 711. So 203 divided by 711 gives us 28.6, on and on for every category in class. This is one of the more complicated topics from these earlier chapters, and it comes up throughout the year, so if you don't get it right now, that's okay. We're really just introducing it. If we're asked if two variables are independent, what we really want to see is one variable affecting the other? If it's not, those variables are independent. So in the context of this problem, does a person's class on the Titanic affect whether or not they live or survive? Right? All conventional wisdom tells us that it does affect whether they live or survive. First class passengers are more likely to survive, and then it goes down with each class. So those two variables would not be independent. So let's go back to that conditional distribution of survivors. Here we can see that 28.6% of the survivors came from first class. And over here, 29.8%, a larger number, came from the crew class. So this seems to be suggesting that you're not more likely to survive being from first class. However, that's not the case. We're just making a classic error of not looking at the full picture. So if we pair this with the conditional distribution of the deceased, so out of 1,490 deceased, 122 came from first class. That's 8.2%. With each step lower in class on the boat, we see that number increase, meaning that your class does affect whether or not you lived or died in the Titanic. So since this is affecting this variable, these two variables are not independent. If they were independent, we would expect this distribution to be the same as this distribution. The information in that contingency table can also be given as some kind of display, for example, a pie chart. So here we can see each class broken up by color. We have the conditional distribution of the survivors and the deceased. If these two variables were independent, these two pie charts would look the same because first class would equal the same proportion for survivors and the dead. Another way to display this data would be something called a segmented bar chart. So we have one variable that's split up by bars, so alive and dead get 1 bar each, and then within each bar we have that same information, what proportion were in crew class, third class, etc. And again, if these were independent variables, these two bars would look the same. So some examples, what percent of females are brown-eyed? This is a conditional probability with the condition being females, saying what percent of females. So we're only looking at the 32 females. We don't care about these 32 males up top. 16 of those have brown eyes, so 50%. What percent of brown-eyed students are females? It's going to reverse the conditioning. Now it's talking about the brown-eyed students. There's 36 of them. 16 of those are female, 44.4%. And what percent of students, there's 64 students, are brown-eyed females? 16 out of 64, 25%. What's the marginal distribution of eye color? The hint is in the name here. For a marginal distribution, we're looking in the margins for eye color, which means we're looking at these numbers and putting each of them over the total number of people in our sample. So that gives us a marginal distribution of 15.6% blue eyes, 56.3% brown eyes, 28.1% other. Conditional distribution gives a condition. In this case, it's that we only want to look at the male students. So there are 32 male students. Take each of these numbers and put it over that 32. Based on the answers to the previous two questions, does it seem that sex and eye color are independent? So we had our marginal distribution, which I have copied and pasted here. Conditional distribution for males is here. If we're checking independence, we want to see, are these two distributions the same? So the same is an ambiguous term. So for example, are these two numbers the same? Obviously, they're not equal, but they're pretty close. It looks like the percentage of people with blue eyes is approximately the same, at least in those two distributions. These two numbers are a little farther apart, and then once we get to this last one, I'm going to call these two different. So for that reason, I'm going to say no, the marginal distribution for eye color is different from the conditional distribution. If these variables were independent, the sex of the student would not affect the distribution of eye colors. You're less likely to be in that other column if you're male compared to an overall student. If you chose to say these are the same, you're not necessarily wrong. You just want to make sure that you justify it correctly. So you'd say, yes, they are independent because the amount of variation that we see in our two samples is really not a surprising amount. All the information so far has been about categorical data, and now we're going to move on to quantitative. It's numerical data based on quantities of how many home runs were hit in a single season by these three players. When it comes to categorical graphs, there's only two options. There's a bar chart and a pie chart. That's it. For quantitative graphs, there's a lot more options. So we'll start with a dot plot. You've probably seen one of these before. For this class, we want to make sure that we have a scale, and we want to make sure that this scale is spaced evenly. So for example, I wouldn't want to put 70 right there because this gap is a lot smaller than all the other ones. I would want to extend my line and put 70 spaced equally. All our graphs should have a title. And for a dot plot, we just take each one of our data points, 54, and we put a dot on the graph at that spot. If we start to have duplicate values, we just stack those dots up like they are right there. Almost any time you're given a graph of a quantitative variable, you're going to be asked to describe the distribution. And you're going to do that with the acronym SOX. The first S in SOX stands for shape. What's the shape of the distribution? So there's a few options. So the first one is unimodal and symmetric. That would look like this. There's one peak, that's the mode. It's symmetric because if we cut it in half and folded it down the middle, it's the same or approximately the same on both sides. We usually want to put approximate before we write the word symmetric. This one here is uniform. It's about the same throughout the distribution. This would also be symmetric because if we fold it, it's the same on both sides. These next two are both skewed distributions. This one is skewed to the left. Think if we started with this graph here and we pulled that tail to the left. Okay, the skew is where the tail is. So that's skewed to the left. This one down here is skewed to the right because the tail pulls to the right there. Next up in SOX is the O. O's for outliers. Are there any unusual data points? So in Babe Ruth's home runs, these two are potentially unusual. So we can say that they appear to be outliers. Eventually we'll go over ways to actually determine this mathematically. But for now, we can just say this is a possible outlier or it appears that it could be an outlier. The C in SOX is for center. We want to represent this entire distribution by a single number. For this one, let's say we pick something right around 46. Okay, it's about the middle, okay, which would be the median. It's also the mode in this case, but we never really pick just because it's the mode. Ideally, we'd like to use the mean. Second place would be the median. It's easier to find. Mode we would pretty much never use unless it also happens to be the mean or the median. The last S in SOX is for spread. We always want to address the variation of the distribution. Is it tightly clustered together? Is it spread out? There's a lot of different ways that we can measure spread. We're going to start with the simplest of all of them, which is the range. And very important, range is a single number. So we wouldn't say that this ranges from 23 to 60. We would say that it has a range of 37. So once we have all that information, we want to write it into a little blurb that includes the context of the problem. Your context is pretty much always graded because stats is a real-world math class, and we're going to use it to solve real-world problems. So we want this explanation to be about Babe Ruth's home runs. If it's just saying the center is this, the spread is this, without mentioning Babe Ruth's home runs, you will lose points. So we would say something like the distribution of Babe Ruth's number of home runs in a single season is approximately symmetric with two possible unusual observations at 23 and 25 home runs. He typically hits, that's the center, about 46 home runs with a range of 37 in a season. So moving on, let's cover all the other types of quantitative graphs we may see. Here we have a stem and leaf plot. Each of our data points are going to be split into a stem and a leaf. So in this table, this is going to split our stem on the left, leaf on the right. We have a title up top because we always need a title. And then we also have a key at the bottom because sometimes this would mean instead of 46, like 4.6. So for a data point like this one, 32, okay, we split it up right down the middle there. The stem is a 3, so it's going in this row here. And then we put that leaf in the table. Okay, typically we want to write these in ascending order, and we want to space out our numbers evenly. So for example, we want this 4 to take out the same amount of space as that 2. So if you can imagine turning this graph on its side, okay, it makes the actual shape of the distribution. So we can see this is skewed to the left towards the lower numbers. The peak is at the right there. There are a few different options that can change the look of the stem plot. Let's start with a split stem plot. Typically we do this if we have a lot of data. We're going to split each stem into 2 different parts. So this would be the lower numbers, 10 through 14. This one here would start the higher numbers in that group, 15 to 19. Then we get to the 20s. So it would be 20 to 24 in that first group, 25 to 29 in the second, et cetera, et cetera. So you can see that everything between 5 to 9 is in that second group of 2s. Everything between 0 and 4 is in that first group of 2s. It gives us a bit of a clearer description of what the shape is. So we can see this is more skewed to the left than it looked in the previous graph. We also have back-to-back stem plots where we can put 2 distributions next to each other. So here's all our stems in the middle of this graph. Hank Aaron on the left with all his home runs, Babe Ruth on the right. And just at a quick glance of that, we can see that they're both skewed to the left. Okay, they're skewed towards the lower end of this data range. And the center for Babe Ruth seems to be a bit higher than the center for Hank Aaron. The most common type of quantitative display is a histogram. Histograms look a lot like bar charts, but the bars are going to be touching each other in a histogram where they were spaced out in a bar chart. The reason that the bars aren't touching in a histogram is because we're not allowed to rearrange this data. If it were a categorical display, say eye color, it wouldn't matter if we put blue eyes first or brown eyes first, but in this graph, it wouldn't make any sense to take this bar and move it over to the left. Any gaps that we see on this display means that there's actually no data in that range. The whole graph is based off a frequency table where we broke our data into buckets or classes, they call them, and we counted how many seasons did Barry Bonds have where he hit between 16 and 20 home runs. 1, 2. Also note that across the bottom here, each number is starting the next class. So it started at 16. This 21 isn't included in this bar here. This goes from 16 to 20. This next one that starts at that 21 goes from 21 up to 25, but not including that 26. All right, there were no seasons in between 26 and 30, etc. The next type of graph is a time plot. Pretty much looks like a scatter plot where the x-axis is time or year. And anytime we look at a time plot, we're seeking out trends in the data. So here we can see that as the years went on, Barry Bonds was hitting an increasing number of home runs. And before we get to this last graph, let's take a look at this frequency table again. It started out as just 2 columns. The class is on the left, frequency on the right. You can see down at the bottom here, the 16. Anytime we have kind of a floating box on the bottom there, that's just saying everything in that column adds up to 16. After that, we have relative frequency. We've talked about this a couple times now. We just take each of these classes frequencies and we switch it to a percentage. So 2 over 16 gives us 12.5%. Write it as a percentage or a decimal, same thing. Cumulative frequency means that we're adding up everything that we've covered so far in the table. So for example, let's look at this one. The cumulative frequency for this class is 3 because up to that point, we've seen 3 of our 16 frequencies. This one is 13 because once we hit that class, we've gone through, if we add up all these numbers, 13 of our 16 frequencies. And then lastly, relative cumulative frequencies. Just take each of these numbers and divide it by the total of 16. So we're going to use that relative cumulative frequency to create this last graph, which is called an ogive. And an ogive tells us percentiles. So for example, there are 0% of seasons where Barry Bonds hit less than 15 home runs. So we start our graph at 15. We put 0% above it to show that if he's hit 15 home runs, he's doing the worst he's ever done. Once we get to this next class, 20, if he hits 20 home runs, he's past 12.5% of all his seasons. So above 20, we're going to put 12.5%. And then just on and on. Each one goes with the one right before it. So here, this one, once he hits 35 home runs, he's past 56.25% of all the seasons, which is about there. Okay, just note that once we get to the end here, this 70 is still going with that 93.5. That's that dot right there. So this one would really go with the next class, which doesn't exist. It's not in the table, but it would start at 75. 75 is called the class width. I'm sorry, 5 is the class width because each of these classes is increasing by 5 at a time. So that's that last dot there. We can answer a lot of questions from Ogive. So for example, what's the relative standing of a season in which Bonds hits 40 home runs? So we just look for home runs. That's across the bottom here. We're at 40. So that would be about there. Over, we'll call that 65. So that's the 65th percentile if he manages to hit 40 home runs in a season. How many home runs must he hit in a season to correspond to the 75th percentile? Same idea, we're just going the opposite direction. So there, we're going to go over. Once we hit our trend line, we head down. So that looks like about 45 home runs to reach the 75th percentile.